Welcome to Strategic Learning in Wireless Networks Theory and Application, Week 3, Tutorial Part Number 3. This week, our focus is on reinforcement learning. So in reinforcement learning, there are a couple of few parts that we need to understand. First one is the reinforcement learning agent. As similar to what we discussed earlier, agent is the person who involved with learning a certain strategies over time. So here in the reinforcement learning framework, agent interacts with an environment via taking certain actions. The goal of this agent is to maximize the cumulative reward, or in some other cases, it could be presented as minimizing a cumulative cost. So based on this agent's action towards maximizing its own reward, he receives a feedback on its own action. Based on this feedback, he tries to explore some other action that could help him to improve the reward, or exploit certain action that could guarantee that the agent is receiving better rewards over time. So in here, the environment is composed of other set of agents or some other interactions. So this environment can be a static environment or dynamic environment. In the dynamic scenario, we model the environment using the notion of states. So this environment generates certain payoffs based on the actions of all the agents. The main difference in this reinforcement learning is that it doesn't require any labeled data. In addition, finding an explicit solution is not something that reinforcement learning is focused on. If we simply briefly look at the reinforcement learning in a static environment, the objective of this agent is to estimate the payoff or the reward or the utility for given action. So simply this could be presented by this analytical relation. So the agent has an estimation that he updates over time, t to t plus 1. And for, how this is done is to take a certain action and receive a feedback. Based on this feedback, the agent weights the previous estimation and current feedback using a certain learning rate, and this weighted sum is used as the new estimation. Now, if we think about how these actions are going to take place, this is. So ideally, it would be to improve the utility. That is the goal. The actions are selected to improve the utility. We call this as exploitation step. When we know a certain action is beneficial, agent prefer to play this action again and again, that in order to obtain the higher payoff. So for example, consider a person is planning to serve a meal for a group of people. Now he has to decide whether she is going to prepare a vegan food or non-vegetarian foods. However, either one of these choices could result in a different payoff depending on the requirements of this group, right? Now, if you think about a different approach, how to select this action, another option is to perturb over these two choices. So here, what we try to do is we try to find the optimal action selection probability that maximize an entropy term. Why? Because this usually maximizing entropy results in equal probability over a set of choices. So in that case, if we go to the same example, what this lady would try to do, she would pick to decide to prepare vegan foods with 50% probability, or 50% chance she would go with preparing non-vegetarian foods. So here, what she tried to do, she tried to randomize over these choices with equal probability. This we can consider as the exploration. So she can decide to explore these two options and see what is the payoff she would receive. Now, if we think about these two choices and how to combine these two choices. So we have a objective to maximize the utility while we have to explore the certain choices. This would result in finding the optimal action selection probability that maximize the utility as well as allowing certain exploration, or we can consider as entropy weighted by a parameter kappa. So ideally, this problem could be presented as like this. So we need to have a probability distribution over certain choice of actions. We can consider this as a mixed strategy probability distribution, and we try to maximize the expected payoff, and this is the entropy term. So this would be the payoff, and here this part is entropy. If you consider about this kappa, now let's consider about when we go for kappa, when we set this kappa equal to 0. So basically what we do, we remove this entropy term. That means we try to maximize only payoff, right? That means we pick the action that we know that is going to provide the highest payoff. However, the question is, we don't know exactly how this environment is behaving, right? If we exactly know, then definitely this choice would be fine. But if we don't know how an environment react to our choices, we might stick with certain knowledge that we have obtained during maybe time t. Rely on that. We try to exploit the action that provide the best reward over time. But what we don't know is whether there will be certain actions we have not played earlier that could result in higher payoff over the time. That is why we have this entropy term. Now, if we consider about this kappa, if we make it very large, so we are going to remove the impact of this payoff part, right? Then our only goal is to maximize the entropy. Maximizing the entropy, usually once we maximize entropy over a probability distribution, the optimal solution would be uniform distribution. So what we try to do here, we try to only randomizing. We are focusing on only randomizing the all the actions. So we give equal probability for every action, and we try to play each action with equal probability and observe the reward over time. By doing that, of course, we know we are there's equal chance to play the best actions as well as worst actions. So what actually we need is to have a balance between these two components. That is why we ended up with this exact objective function. Now, as an exercise, you could try to play with, try to solve this optimization problem. Then you are going to end up with the optimal solution. Beta is given by this. Okay, this is defined for all actions, right? This distribution is known as Boltzmann distribution or GIST distribution. This the advantage of this distribution is it allows exploration and exploitation of all the actions, satisfying this condition. One key important thing that I have to explain in here is the impact of this learning, right? Sometimes we need certain updates, certain iteration or certain steps has to allow agents to learn something faster than the other. So in that case, this learning rate plays a major role. Now consider a simple example where we calculate the time average value x bar in this format. So we have time average value or an estimation that we observed at time t, and we have new observation. Notice that there is no bar notation here. So this is a new observation at time t. So what we try to do actually, we have x bar t and we have xt. We try to do the weighted sum. Lambda times this 1 minus lambda times the whole term. So this is what we ended up here. Suppose this is the way we are going to update our new time average estimation of x. Now, if we think about this this step, if we set this lambda is equal to 1, so basically we neglect whatever the knowledge we had accumulated over time. So when lambda is equal to 1, x bar t plus 1 would be just xt, right? So we simply neglect what we had already. We just take whatever we observed at time t as the new information. So that means we try to update our estimation with the recent knowledge. So we are exploring all new actions and take that information as the information that we would need to keep with us. In the other extreme, when lambda goes to 0, our x bar t plus 1 is going to be simply x bar t, right? That means we always neglect this information, right? So basically, what does it mean? We assume this time average estimation x bar. This is something that is not going to change over time. So if we know this is if we know this is the exact estimation when t goes to infinity, then we don't need to worry about this part, because we know whatever the instantaneous values over time, they will be average over to x bar. So basically in that regime, it means we know the expected payoff. Based on that, we know what it would be the best action if we consider matching this into the response and the learning scenario. So here we use the knowledge of history, and then we try to exploit. At this region, what we do, we neglect the history, we use the current value, and we explore over different choices. So somewhere in between allow us to combine exploration and exploitation together. Why I explain this part? So now if you go back to this reinforcement learning over static environment scenario, with optimal action selection probability obtained from this Gibbs distribution, we can update our strategy over time following this equation. So what we are trying to do, we have a probability mixed strategy at time t. We observe the best strategy based on the reward received at time t. Then again, we weight our previous knowledge with current knowledge and update it. It is quite similar to what we did in this utility. So we try to here we try to estimate the payoff over time. Here we try to estimate the strategy selection probability over time. Now you can see the learning rate here, lambda t and mu t. They are not identical, right? They are two different things. If we think about how these steps has to be done, ideally we prefer to have this knowledge about the estimated utility. We need to gather this knowledge much faster compared to this update in the action selection probability. Reason is, once we know this estimated value accurately, then we can update this probability with higher confidence. Therefore, we need estimating the utility needs to be faster than estimating the updating the probability. So this condition is satisfied by this requirement. So our choice of lambda and mu needs to satisfy this relation in order to obtain a fast convergence in estimating the utility compared to the action selection probability. In addition, these tests could result in a converged solution. We need these two, or at least these four conditions for both learning rates. So here, if we take the summation over the learning rate from time 1 to infinity, this needs to be diverged. Summation should be diverged, but the summation of the square term needs to be converged. So this needs to be satisfied both lambda and mu, while satisfying this condition for faster. This condition is to ensure that utility estimation is faster than the probability update. Now, this is one simple exercise that would give you some idea how to pick these learning rates, satisfying these two conditions, right? So now the question is, show that a learning rate given in this form with alpha in between half and 1 satisfy the convergence condition. So let's write down the convergence conditions. So first one is summation from V1 to infinity. This should be diverging. Sorry, this goes to infinity, while the summation of square terms should be a finite value. This is the condition. Now we can try to pause the video and try to work out this. Then come back here and we will do it together. Okay, if you have tried it or if you want to know the technique. So I'm here, I'm trying to use a graphical approach to solve this problem. Now, if you think about these values at each iteration t, this is t here. At t equals 1, we have 1, right? At 2, we have 1 over 2 to the power alpha. So we can say this is 1, this is 2 to the power alpha minus alpha. At 3, we have this 3 to the power minus alpha. So you can notice simply this is 1 over t to the power alpha expression. Now, since this series is quite difficult to add up, what I'm trying to do is here to consider this behavior in a continuous domain. Now, if I match these points, what I can easily draw is a curve 1 over, since it is a continuous domain, I'll write it in terms of x, although this is in terms of time indexes. I can write this as 1 over x to the power alpha. We know if I integrate over this function for a given duration, at least I can calculate the area under this curve. Now what I'm going to do, I'm going to make a couple of rectangles at these points, right? So they will appear. So if we consider this, all of these rectangles, they have a width of unit 1 and the height corresponding to 1 over t to the power alpha. So the area of the one of any randomly selected this rectangle would be 1 over t to the power alpha into 1. So technically 1 over t to the power alpha. So our summation 1 over t to the power alpha t equals 1 to infinity. If I consider this as S, this is equal to sum of areas of all the rectangles, right? I guess this could be given as summation of all these rectangular areas. We can see that 1 over x alpha curve is below the area under this curve is slightly less than this summation. Why? Because you can see these parts and this one and again this part. They are some excess points if we remove the area under this curve. So what we can say, if we integrate this 1 over x to the power alpha from 1 to infinity, we know this s is larger than this quantity. Now consider the same case, because now since this is this height of any general rectangular shape is, as I mentioned, it is 1 over t to alpha. So this height is also going to be the same, right? And this height is equal to the height at this point, right? So similarly, I can move this 1 over x alpha curve to this point. So simply what I did, I shift this graph toward here. So this one should be 1 over x minus 1 to the power alpha. So that curve passed through these points. Now if I draw it in a separate figure for sake of clarity, if I draw, okay, like this, I can see this is 1, 2, 3, 4 likewise. If I consider from this point onwards, the area under this function over here, 1 over x minus 1 to the power alpha, area under this curve, if we remove these squares from it, you can see there are small parts that are going to remain as the excess values. So we can say this area is equal to, because yeah, from here to here, if we consider this rectangle, they are going to be s minus 1, because you know this area is with an area of 1. The height is 1, the width is 1, so this area is 1. However, we are integrating over this one from 2 and onwards. So if you consider the integration of x minus 1 power alpha from 2 to infinity, and if we add additional 1 from this rectangle, this summation is larger than s because of these small areas that are going to be as excess parts. So we are going to end up in here. Now we have this condition. Okay, if you consider about this part, I can change the variables. Like if I change x minus 1 into x, I can write the same expression as. So if you are confusing, we can say just we say y is equal to x minus 1. So dy is going to dx, and the limits are going to change when x goes to 2, y goes to 1. When x goes to infinity, y goes to infinity. So basically we can write this expression as 1 to infinity 1 over x to the power alpha dx s, and again we have 1 over x to the power alpha dx. Now since y is a dummy variable, I'm replacing it by x plus 1, right? And we just need to focus about integration of this part. You know, when alpha is equal to 1, this is equal to ln x. Ln infinity is infinity. So if alpha is equal to 1, we are going to end up here. Now, if alpha is for any other values, we know this is going to be so this x to the power minus alpha. We can consider this as x to the power minus alpha plus 1. Sorry, divided by minus alpha plus 1. 1 to infinity, right? For any other, right? So yes, minus 1. Yes, we are going to end up here. Now we can consider about two parts from here. When 1 minus alpha is positive, so we can, which means when alpha is less than 1. So it means when this is positive, this is x to x. When substitute infinity to x, infinity to power positive value is going to be infinity. So here it is going to be infinity, right? When alpha is larger than 1, this is negative. 1 minus alpha is a negative component. So when we substitute x by infinity power negative power, this part goes to 0. Then we ended up minus substitute 1. So we can consider it as 1 over alpha minus 1, right? So we are going to end up with these three cases. Now let's see where we can write the rest. So now we have these results. By this step, we know when alpha is either equal or less than 1, this part goes to infinity and this part goes to infinity. So basically S is unbounded, right? By looking at these two sections, we know when alpha is less than or equal to 1, yes, you can see S goes to infinity, because this is this theorem is known as sandwich theorem. So your lower bound goes to infinity, your upper bound goes to infinity. So basically S needs to go to infinity as well. Now you can see if when alpha is below 1, right, we can see S is bounded by 1 over alpha minus 1. Sorry, this is below. When alpha is larger than 1. And here 1 plus this term, it is going to be alpha over alpha minus 1. So any positive, any alpha higher than 1, this is a finite value, this is a finite value. So basically S, we can say S converges to a finite value. Here S diverges. So that these two results say choices of alpha that could result the summation to diverge and the converge. Now if we look at our conditions, convergent conditions, it says summation should diverge, right? In order to diverge, in order to the summation to diverge, we need to alpha this condition, right? So sum lambda t equal to infinity. For that, we need alpha should be less than or equal to 1. Then we have the second condition, lambda t square. This summation should be converging, right? Now if we consider about this lambda t square, this is going to be simply 1 over t to alpha, right? Because lambda t is 1 over t alpha, then this one is 1 over t to alpha. Since this is converging, we can see the choice of 2 alpha should satisfy this one. So basically it means 2 alpha should be larger than 1. So we are going to end up with our alpha should be larger than 1 and less than equal 1, right? But let me see. Yes. So I think this should be like this then. Can double check, yeah. So a choice of alpha between half and 1 would result 1 over t to alpha kind of a rate to diverge when we take the summation over just these terms, and to converge when we take the summation of the square terms. That concludes this exercise. Now let's focus about single agent RL in dynamic environment. Usually these cases are modeled using a Markov decision process. A Markov decision process, an MPD, is composed of 4 components. Then first part is set of environment states, then set of agents action, set of agent actions. So here one agent, and a reward function which map this strategy, sorry, the state and action to a real value function, real value reward, and finally a state transmission probability, which says transition from one state to another with given probability. So the objective of this MDP is to find a good policy that map the state to a certain action, or the state space to action space, that maximize the expected discounted reward. Here the reward is R and gamma is a discount factor, right? This is considered as expected reward that could be over finite t or infinite time horizon. So one simple example is given like this. In this problem, the environment has 3 states, S0, S1, and S2. The agent has two actions, A0 and A1. This graphical representation provide for any state, a choice of certain action would result in a change in the state with this probability. For example, if you consider about in state 0, the agent taking action A0, there's a 50% probability that the agent is going to observe it is in again in the state 0, or there's another 50% probability the state is going to change from S0 to S2. So similarly, if we consider about agent is taking action A1, this indicates there's 100% chance that state is going to change from S0 to S2 when the action is A1 is taken at S0. Now you can notice that in state 1, again, the agent has same two choices, but these two choices would result in different probabilities to reach certain environment states, right? It is not similar to this one. And this orange curve shows the reward. So whenever there is nothing, you can consider there is no reward for all these steps, while you can see when the agent is at state 1 and taking action A0, then he will be he will be rewarded by 5 points, and the state is going to change to S0. If the agent, if the environment state is S2 and agent takes action A1, there's a possibility that he will be the state is going to change from S2 to S0. In that case, he will be rewarded by -1. So it is kind of a penalty. So the state transition function, we can say this is a graphical representation of this state transition function, or we can consider about matrix form of state transition function. So let's say for action A0, we can consider changing from state 0 to state 0 is 50% probability. So from state 0 to state 1, okay, there is no chance, so 0 probability. And from state 0 to state 2 is 50%. Similarly, if you consider about if you when the environment is 1 and action is A0, with 70% probability it goes back to S0, 10% probability that is going to stay in the same state, and remaining 20% probability that it goes to S2. Similarly, you can check for S2. Now, if you consider about action A1, again, you can follow the same logic, and this matrix says what is the state transition probabilities. Now, when this Markov decision process is going to be RL, so when the policy or the transitions are unknown, we can consider this Markov decision process can be considered as a reinforcement learning problem. So two important additional things that we need to know when we go for this RL environment is the state value function. So the state value function defines the reward that is going to be received for the agent following this policy phi when the agent started from state S. So he started from state S and he was following the policy phi. So most likely he might go to S1, let's say then S3, then S2, S4 likewise. So this is how the states are going to change over time based on this policy. And here can consider the reward accumulated at this point is going to be the state value function, right? Yeah. Other important function is the action value function, which is also known as the Q function. So this Q function says the received reward for choosing action A at state S. So this is not aggregated over time. It is about the reward for choosing action A at given state S. Still, this choice of these actions are followed by this policy phi. In the Q learning, what agents try to do is it's try to learn the quality of certain actions. So the Q function or this Q value for given state and action gives the quality of the choice of this action. How beneficial this action in order to improve the expected reward. And the other advantage is this model does not consider about any information about this Q learning does not need any information about the environment model or analytical model. So this Q learning is a model-free function, so which can be easily adapted for many use problems. And this since this one consider about the environment with dynamic states, this Q learning is suitable for stochastic problem. So how this Q value is updated over time? So it is given in this equation, which is quite similar to what we have observed in previous slides, but there's slight difference here. You can see this is the Q value of playing action AT at status, or we can say the action A and state S. Suppose this is the Q value we know at time t. So this is the old value. So what we are trying to do, we are trying to find what would be the Q value for the same choices at t plus 1. How it is going to be updated? Again, it is going to be a weighted sum over two components. One is the old value. The second one is based on this part. So here, these two terms. Here, RT is the observed reward for taking certain action, and you observe the reward. However, this part is providing the best outcome from the next choice. So we know what we are trying to do. Okay, the next state is st plus 1. At that state, we have so many choices we can make. Out of all these choices, we would result in a different Q value. So we are going to pick what could be the pick the action that yields the best Q value at a state t plus 1. So out of all the actions, we pick the best Q value, we discount it by this discount factor, add it into the reward, and use it as, let's say, the Q value kind of observed at time t, and weight it with Q value that have been observed over the course of duration, and update the Q value for t plus 1. This is the main step behind the Q learning approach. So for this Q learning, why we need to crack this, because this cube value help us to determine what could be the best action that we have to take along the path to ensure we get the best expected reward. Now let's check one example and see how this works. In this example, the goal of the agent is to find the best route to go outside from any starting position. So suppose the layout is given like this, and we have numbered the rooms from 1 to 5, and the outside is numbered as number 6. So the idea is agent starts from any room, and whenever he take an action, so either he decide to stay in a room or decide to go to a next room or go to a next room outside, it cost -1. However, reaching outside will grant a reward of 11. The question is how to find the best route starting from any room. In this, given these values, we can consider about creating a reward matrix. And here I have done it using a MATLAB environment. So you can see in the columns here, let's say this is the starting location, and here we have next or the target location. You can say the target should be a next location. Also, similarly, instead of location, we can consider this as a current state, and this one as the next state. Now, one example, if the current is 1 and the next state is 1, so the decision is to stay in the room. A -1 will be rewarded. Only other option is to go to room 5, this one, which will again grant -1. So these not numbers are the options that this agent cannot make. So you can see, for example, if we consider the room number 2, the choice is to stay in the room number 2, move to room number 4, or move to let's say room number 6 or outside, which will grant 11 points -1 would result in 10 rewards. So similarly, you can generate this reward matrix. For starter, I initiate the Q value matrix like this. So you can start from 0, but I just wanted to make sure in order to in order to normalize this matrix and do a somewhat clear representation. Now, what we will do, we will pick a random starting position. Suppose in this run, but I have picked a position, random position 2, and make a random decision. So my decision and the next state is going to be same, because that now here the first one of this random draw has happened to be like this. So first draw, I decide to move to room 4, then move to room 5, then move to room 1, again from 1 to room 5, then 5 to outside. So while I doing this, I'll try to keep updating the Q values based on the equation that I have presented a couple of slides earlier. So by using the simulation, I got this set of results. So I started from this one, then moved to room number 4, moved to room number 5, number 1, again room number 5, and came back to room number 6. So by the end of this first training round, so the end, I mean, we have reached the goal. So we have a couple of places updated, but some places we haven't explored. As an example, staying in room number 2 is not explored in this run. So therefore, the values have been not changed. You could have consider about moving from 2 to 6 in one step, which could reward a high value, but that has been not explored in this scenario. Next, what I did, I run this kind of similar setups for iterations, like similar training iterations over 10 times, and the final results or after each iterations are shown like in these figures. So in order to clear representation, I have scaled the Q value matrix. So at the beginning, you can see. So to interpret this image would be the lighter the color, there is a more reward of choosing that one. So at the beginning, there is not much of difference of these choices. However, as time goes by, certain actions or certain choices start to appear better over time. So now let's see, after this training, because this is still the training phase, right? Now what would happen when we go to the inference phase? Suppose we start from room 1. So out of the options available in room 1, staying at here or move to room number 5. Out of this, we can see this one had higher Q value. So our choice is to pick room number 5. So once we reach room number 5, out of all these 4 options, we can see moving to outside, you the best reward or the Q value. So we pick this one, leading the agent reach to outside. Now consider we start from room number 3. Out of these options, you can see moving to room number 4 is better than staying in room number 3. So we pick moving to room number 4. When moving move to room number 4, it happens to be that the best choice is to move into room number 2. Okay, one could ask why moving to room number 5 is not so good. The reason is our training has done only over 10 iterations. So most likely over these 10 exploration phases, we might end up with choosing this path, which happen to be providing higher chance to go outside compared to the choices that this agent has made during the training phase. So most likely he might end up with moving to 5, moving to 1, coming back to 5. So basically he end up with having much higher cost of going outside compared to this selected route. So that is why he decided to move to room number 2. Once moved to room number 2, it has to be shown that moving outside would be the most beneficial. So in that way, the agent decides to move outside from the room. So now we have discussed about only one agent. What happened when we consider about multiple agents? So we can extend this Markov decision process defined for single agent to multiple agent via generalization. Therein, our Q value updates is now defined for agent N, and the action is based on the action made by agent N. However, for the reward, it accounts action of agent N as well as all other agents as actions of all other agents. So altogether, the reward is determined. And the best outcome and discount factor is similar to the previous case. Now the question is whether this is going to work. This requires agents to observe the true state, but with large agents, it is not guaranteed that all agents can observe the global state. In that case, they are limited to their local view. Then it has been found that this queue update might not result in the optimal decision. Another key aspect is that what could happen with increasing the number of agents, the action space and the state space start to grow. With such large action, such large dimensions, it will be challenging to track these Q values for each action state there. This is commonly known as the curse of dimensionality. Higher the dimensions, it is challenging to track these values. In the literature, we can find many reinforcement learning algorithms. Some are defined for discrete state spaces and some are for continuous state spaces. We have already discussed Q-learning, where we consider all the state, action, and reward. Based on that, we predict, we consider okay, what would happen in the next state. Those are the information that used for in the Q-learning. And there's another variation in Q-learning, SASA. In here, they consider state, action, reward, state, and corresponding action. So the difference is in Q-learning, we consider the choice of the action that would grant the highest Q value, whereas in SALSA, we consider just one action and use the Q value based on that action, not just the action that provide the best Q value. And another option is the Monte Carlo simulation, where we do the sampling, the policy iterations, and use the sampling mean. In continuous state space, most popular one is deep Q network. Here, what is done is that the Q function is approximated via nonlinear functions. Then there are actor critic methods. DDPG, A2C, A3C. What is done in here is we use an actor network model and a critic network model, where actor make the decisions and the critic criticize those decisions. So basically, actor decides what is about this action space, and critic generates the values of rewards. So basically, the value function is handled by the critic, and the state and action function is handled by the actor. In addition to that, there are many more algorithms you can find in the literature. Now, let's check a couple of applications. The first one I'm using here is upward balancing pendulum. This is an example. You can find it in from MATLAB. The code is a code, and the results are can be analyzed in MATLAB. Here, what is happening is that you have to find the torque that needs to apply to balance the pendulum in upward position. So the scenario is like, okay, we have a pendulum and we need to apply a certain torque. With the torque, the goal is to reach this position and keep the pendulum in the upward position. So reward at any time t is defined in this manner, where theta is the angular displacement. I think it is with I think here, and theta dot is its derivative coefficient, and u is the control effect. So it is related to the tau. So after training here, this problem is solved via deep Q networks. So I have gathered two scenarios. First one is when the network is untrained, or actually it is trained with few iterations, and then I have run about like I think it is about 100 different iterations, and the network is fully trained. So it's basically this is the inference phase. So let's see what happened in untrained environment. So you can see the torque is slightly varying, and you can see pendulum is just moving. So this is what happened in at the very beginning of the training phase. While doing that, the Q value is refined over time, and by the end we get a fully trained network which behave in this manner. You can see the torque has been changed a lot, then stable, then it reached to a certain point where the pendulum is stabilized. The next example is one of work we have done in millimeter wave communication of vehicular network. So here the scenario is the roadside units, they deliver infotainment content. So they have information as well as video data to vehicle user using millimeter waves. So ideally, not ideal, the baseline is to serve these users by a single roadside unit that needs to estimate the channels in periodical manner, and based on that, it can serve several vehicles. In this paper, the idea is to make decisions beforehand and try to align these beams to enable multi-connectivity at the vehicle user. And the problem is the prior knowledge on the channel model under this network dynamics, it is not available. Therefore, here a reinforcement learning technique is used to generate policies for each roadside unit to align the beams and enable multi-connectivity at the vehicles. So they are in there are two. They have in here this actor critic approach is used to solve this reinforcement learning problem. When I generate the policy in actor network, so actor network generates the policy while the critic network generates the values. The reason is we don't have the actual models for this policy and value generation. So in this case, the states are considered as the past channel observations, and for URLs type users, they are considered about violation of rate drops below a certain threshold, and for EMBB type of users, they are considered expected rate or the average rate as the input. So the training has been done in online where with training has been done in offline manner. So considering a different environment and training this network at each base station separately, and during the online inference phase, this base station operates simultaneously. So one example that results is sorry. Here for this deep reinforcement learning technique with offline and without offline offers highest data rates for the users, while proportional pair or the allocation based on maximum channel and without a reinforcement approach try to solve a optimization problem at each time interval. All three where these baselines indicate poor performance in terms of maximizing data rate at the vehicles. The last example is again for the vehicular network. Here, the scenario is focused about autonomous or driver-assisted vehicles. The idea is like these control decisions at each vehicle are based on the field of view of the vehicle. And this field of view is defined in terms of the sensors integrated in the vehicle. However, it would be nice if we could extend this field of view using the information gathered from other vehicles. So if these vehicles can share their view as a 3D map with each other, each vehicle can make their own decision with much higher efficiency. But the problem is this real-time high-definition map sharing require lots of radio resources, which is quite impossible to have under this kind of a dynamic environment. So the solution is to train a policy that allow the roadside units to allocate the resources among vehicles and ensure the connectivity among the vehicles, which says, okay, what information has to be exchanged with each other with which resolution. So here we can say the resolution in terms of a vehicle can send one huge area as a single chunk, or it can further divide this into several small areas and use one packet to send information in this small area. So either the vehicle can decide to send one packet assigned for the large area, which means low resolution, or a packet of data based on a small area, which means the high resolution. So vehicle has to make a decision what information that has to send to the other vehicle depending on the interest of other vehicles, right? Although I am not going for details in this case, those who are interested can check this paper. I would like to highlight a couple of results based on this work. So here, instead of using conventional actor-critic design or deep QAN design, the work is focused to use branching technique. The advantages of this branching technique is these choices of vehicles produce large state space and a large action space, which means it is quite impossible to track all the state action combination. Therefore, this branching approach allows these reinforcement learning agents to just focus on certain branches of, let's say, if you consider a Q table, this branching allow us to vehicles to focus certain areas and try to train over these areas instead of focusing on the entire Q table. From the results, it could have seen that when vehicles use training, it can provide higher rewards for most of vehicles relatively and with higher rates, whereas non-trained agents are limited to higher data rates but very poor rewards. Next, here the work compares the proposed branch-based deep Q network with traditional deep Q network. This branching, the branching technique, which allows to analyze certain sections of queue tables, rather the entire queue table, allow to learn the better policies with much shorter time, yielding higher rewards compared to traditional DQA design. So that's all for the reinforcement learning tutorial.